as the title says, I'll be talking about reasoning, attention, and memory. So, yeah, I don't know, like just to give you a bit of a story, like as a not as old as Joshua, but I've been working in deep learning since I started my PhD in 2003, and I attended a couple of machine learning summer schools when I was a student, and it used to happen in University of Toronto then, again sponsored by Cypher, and the room used to be full, like as it is right now, but only composed of these two rows. So it's fascinating to see how the field has taken up so much so fast, and so much has been done already in 2 years, which looks like eternity. So yeah, so as the topic of my talk, as the title says, is reasoning, attention, and memory, where Joshua gave a really brief snapshot of things like memory network, attention based models, etc., which have recently basically come into the limelight, and they seem to show a lot of promise in a lot of interesting, challenging problems. So just to give you a bit of a motivation, deep learning, as we know, is pretty successful at vision, and you see the basic architecture might look something like this, where you have a convolutional network or some derivative of this network. You pass in an input image, and which goes through a bunch of hierarchical feature transforms, and in the end you get like a feature vector on top of which you plug a classifier for your final objective. And the final objective could be object detection, it could be object recognition and stuff like that, and deep learning models we know are the state of the art. And something similar has lately happened in speech as well, where basically you have an acoustic signal which sort of is sampled at some frequency to get your input spectrogram, which can be viewed as a two-dimensional image. And that image is plugged into, again, a deep network, and the network essentially predicts the phones at every frame, and then you can plug your language model and stuff like that to stitch these phones, the predictions of the network, and finally what you get is the output sentence that has been spoken. And again, like models like these, of course, like what goes in here, I'm not going into the detail, but the models like these are sort of almost state of the art in speech as well. And something similar has happened in the domain of text, although it's still a little it's still catching up, where basically you have an input, you featureize your input in some way, and you have some deep network, which could be a feed forward net, a recurrent net, or like an LSTM, a GRU, and in the end you have some objective, like some task at hand. In this case, I've shown a sentiment analysis task, where given a sentence you want to say whether the sentiment of the sentence is positive or negative, or it could be any task, any standard NLP task. So the question is this enough? Before that, so the general basically formulation is you have an input, you represent it in some way, you have an encoder or the feature extractor which extracts the features, and then you plug in a classifier, a regressor which we call a decoder, and you optimize the whole thing using some loss function, right? And the question here is this enough, basically, right? So let me give you a couple of scenarios where basically we'll see whether it's enough or not. So suppose you're given a story, like a really simple story of an actor called Joe and maybe Fred, and they do a whole bunch of tasks like moving around, picking up objects, etc. Like Joe went to the kitchen, Fred went to the kitchen, Joe picked up the milk, Joe traveled to the office, Joe left the milk, and blah blah. Now, if I ask any human to answer these questions, where is the milk? It's not hard to sort of infer from this story where the milk is. Probably as a human you'll see in the story where the word milk appears, and you know that the Joe had left the milk. And where did Joe leave the milk? basically Joe traveled to the office in the last previously before leaving the milk, so highly likely the milk is in the office, and yeah, it is. And likewise, where is Joe? You can infer from the story it's in the bathroom, and where was Joe before office? And again, you can infer that he was in the kitchen. So, like tasks like this are fairly easy for a human to answer. Consider scenario 2, and this is like a sort of an exercise for you guys. Basically, you are given a story of 20 sentences, like some snapshot of taken from some random book, but these 20 sentences are sequential, and I show you the 21st sentence with one of the words missing. So I give you 1 minute to read the story, and let me know what the answer is. Right. So how many of you think the answer is Mr. Cropper? How many of you think the answer is Mr. Baxter? Okay, that was pretty bad. Come on, this is like an exam. Okay, well, let me give you the answer. The answer is Mr. Baxter. Right. Anyway, so maybe not under so much stress. If I had given you enough time, you would have read the story, and probably with a very high likelihood you would have answered this correctly. Right. And scenario number 3. Now, suppose you are given a whole knowledge base, of facts, basically as a set of triples where you have an entity, some action, and some relation and another entity, and you have millions of these facts. So you want to store them, and then you want to ask questions like who wrote Kung Fu Hustle, or even more complicated questions like I'm interested in watching a Stephen Chow movie other than Kung Fu Hustle, can you suggest something, right? So, and even like yet another scenario of dialogue modeling, where you have a user who's chatting with a bot, and user has an intent of making a reservation in a French restaurant of table of 6, and basically the restaurant should be sort of a high end, and then the bot indulges in some sort of an interaction like where the location should be and stuff like that, and at some point the user wants to revise his or her preferences of going from 6 to maybe 4, and then the bot needs to keep track of whatever else it had sort of known about the user's intent, and then modify subsequently and finally make a reservation the way a normal human would do, right? So basically the scenarios, like these 4 scenarios are shown so far, cannot really be modeled as an input-output mapping from X to Y, where X is your input, potentially your stories and your question, f of W is basically your standard deep net, some parametric model, and you want to sort of give the right answer. Basically, there's sort of a need to have some sort of an external memory, that sort of external persistent memory that remembers the context, right? And given this memory, which could potentially be huge, your model should know how to look, like given a question, your model should know how to look, or rather where to look into this memory. And not only that, it should know what to look for in the memory. And given a short list of memory slots that your model might figure out where to look at, the model needs to reason. Basically, in the example, in the toy example of Joe going to the office and dropping the milk, I mean, the model needs to know what does going to the office mean and what does dropping the milk mean, and so on and so forth. And it essentially needs to handle, like this context is huge, and it could potentially be changing, right? So in short, we really do need some sort of a memory that is augmented to this function f of w, which can enable answer in these complicated scenarios. So one might argue, given the previous talk from Joshua about RNNs, that the hidden states of RNN, particularly LSTM or GRU, are effectively memory. So why not just simply run an RNN on your external context and get some sort of a representation of your story and use that representation to map questions to answers or responses. But clearly this will not scale, as Joshua mentioned, because of primarily two problems. One is the vanishing gradient, and to an extent exploding gradient, but that can be handled. But primarily it's the vanishing gradient, or in other words, RNNs don't really have the ability to capture really long term dependencies. Like if I give you a knowledge base of 1,000,000 facts, there's no way an RNN can hold all the facts in its memory. One, because of the vanishing gradients, and two, because the state of the memory is like really small. I mean, even if it's like 1,000 hidden units, there's no way you can expect to store such rich information in those 1,000 hidden units and reason with that, right? So, which brings me to the topic of my talk. Basically, recently, in order to answer such questions, there have been a bunch of models that are proposed in this direction, namely memory networks, which I'll talk in quite a bit of detail. And basically, I'll go over various versions of these networks. And then around the same time, there was another sort of model that was proposed called neural Turing machines, which does something similar, but it was shown to do interesting toy tasks, and not until recently it has been applied to some essentially a real world problem, if you want. And then there is also another set of work which is somewhat old, but recently it has again seen a resurgence, namely basically augmenting your RNNs with external memories like stacks, lists, and queues. So if time permits, I'll talk about the third set of models, but if not, then it's okay, because tomorrow probably you'll hear about them in quite a bit of detail, right? So yeah, so the general architecture of all these three classes of models can look something like this. Basically, you have a controller, which is, think of a controller as like a standard deep network. Could be a feed forward, could be an RNN network, could be anything, which has multiple tasks. Basically, not only it produces the output y, but it also controls your read and write head into the memory. And then the main component is this memory bank, which will store your context, the stories, the knowledge base, etc., etc. Right. So the purpose of the head, the purpose of the write head, as the name suggests, is given the input and essentially the output of the controller, it sort of decides which fact to write where and how. Likewise, the purpose of the read head, as the name suggests, is given the input x and the sort of input of the controller, which part of the memory to read and pass the information back to the controller. And finally, the controller, once given an input x, it will basically read some stuff in the memory, write some stuff in the memory, read it from the memory, combine it with input x, and do some processing to finally generate your output y. So all of this will become clearer with an example, but that's the basic architecture. So what distinguishes the three architectures shown in the slide are basically what goes inside each of these components. Like what sort of memory are we using? Are we using a tape? Are we using a stack, queue, whatever? And what are the functions the read and the write head, and what exactly is a controller? So memory networks is one version, neural Turing machines is another, and so on and so forth. Right. So yeah, so basically let's go deep into what a memory network looks like. Basically, it's a class of models which combines, as I said, large scale memory with a learning component, and you can read and write into the memory, and it incorporates reasoning over the memory via this notion of attention. So, I'll talk briefly again about attention today, but you'll hear a lot more in detail in tomorrow's talk. And the cool thing about memory network is that the framework is flexible enough to store rich representations of your input, right? And the model is scalable in the sense that the memory can potentially be massive, and still you can efficiently do reasoning. How? Like again, I'll speak as over the course of my talk. And yeah, and lastly, again, as I said, like the whole specification of the memory network model is flexible, that you can store basically long-term memories, you can store short-term memories, and a combination of these can help in solving tasks like dialogue modeling, etc. So, how so just to give you a brief overview of what the processing steps of the memory network look like. Basically, given an input x, the first step is for the controller to convert the incoming input into some internal representation. So, in the original paper, this was denoted as the module I, the input module. And then the write head the step 2 involves the write head updating the memories and also writing the new internal feature representation that you got from step 1 into the memory. And the step 3 involves, given this external input and the contents of your memory, the read head will read some portion of the memory and pass it on to the controller. And finally, the step 4 involves the controller doing the remaining work. Basically, it takes as input x, it takes as input whatever the write head, the read head read from the memory, combines the two to finally answer your question, right. So, let's be a bit more specific with respect to one simple example, which is similar to the story that I told earlier. Let's go into a bit more specifics using a specific story. Basically, the model is given this simple story: John was in the bathroom, Bob was in the office, blah blah blah. This is what's called a context, right? And during training, what you're given is this question answer pair based on that story, where the question is where is John and the answer is kitchen. And in addition to that, in what the very first version of the memory networks, what we call the fully supervised, in addition to these two things, during training you're also given this so called supporting fact in the story, where basically it tells you which sentence in the story has your answer or has some signal associated with your answer. Of course, this supporting fact is not given to you during test time. So, yeah, so during test time you're just given the context and the question and you want to generate the answer. So, step 1 of a memory network would involve storing the representation of the context. Now, what goes into the representation is entirely up to you. Like there's no sort of restriction on what it could be. Like it could be individual words, like you might want to store individual words of the story in each single memory slot, or you might want to store a window of words in each memory slot, or you might want to store the whole sentence in each memory slot, where again the representation of a sentence could be as simple as a bag of words, where you essentially take the average of the embeddings of all your words, or it could be an output of an RNN, or it could be an output of a CNN, and so on and so forth. So this function f basically, which takes as input a sentence, a sequence of words, stores and outputs a memory representation which is stored in the slot, and this is quite flexible. now you're also given a question during training, so you do exactly the same thing. You represent the question as x via the same function. The step 3 of the memory network involves defining the so-called scoring function, where essentially the task of a scoring function is to measure the sort of a relevance of each of the memory slots with respect to the question, right. So, the scoring should be in such a way that the memories which are relevant, like, well, before that, like the scoring function typically is a parametric function. It could be a neural network or anything, but the training of this parametric function should be such that in for all the relevant memories, it scores the score that it gives with respect to the question is higher than the score with respect to irrelevant memories. Yeah.
I could not get what is the difference between supporting fact and the context. So these sentences, 4 sentences here, are those context or are those supporting?
So the 4 sentences are the context. The supporting fact is the subset of the context which is the most relevant based on your question.
But at test time, I don't know which is the most relevant, right?
Yes, you don't.
For the network to figure it out.
Yes, exactly.
But at training time, we provide annotations for which is the most relevant.
For this version of memory networks, which we call fully supervised, but I'll talk in detail later about another version where you do not even need that during training and where it automatically learns, right. So, some of the example choices of a scoring function could be like a simple input output mapping via some transformation matrix U, which is basically the learnable parametric matrix, or as I said, it could be a fully connected network that takes as input the question and some memory slot and generates a score. Again, it's up to you. And step 4 finally involves designing another parametric function which maps the current question and the relevant memory that you obtained from your read head, basically the memories that gave you the higher score, and use these two information to generate your final answer, right. And in the first set of experiments, this was basically again a scoring function where basically we scored all the possible responses given the input and the memory and picked the one that gives you the largest score, right. And assuming that you've trained your function f, your parametric function that is used to generate the answer, the scoring function, and basically the memories, then given a question at test time, you will score it against all your possible memories and you'll pick the highest memory and use that memory in your final parametric function to finally generate your answer. And all of this is achieved by minimizing this following loss. So I'll just go briefly explain what this means. So the first term essentially says x is your question. You basically want to score the memory which is relevant to you, which is given to you by the way as a supporting fact, to have a higher score than all the other memories f bar by some margin gamma. And once you have that's the first bit of the scoring function. The second bit of the scoring function says the loss function says that given the relevant memory and your input x, you have another scoring function SR, which essentially increases the score of your correct response R and decreases the score of all the incorrect responses R bar. And as one of you asked, basically how do we know this? So as I said before, in the fully supervised setting, we are given access to this during training time, right? So that's pretty straightforward. So it's like a standard margin loss where you want to increase the score of your correct memories and decrease the score of your incorrect ones. And as you would note, this loss function essentially will work when you have a single supporting fact. what do you do when you have multiple supporting facts? Where given this story where basically you're asked the question, where is football? You first need to know that John was the person who picked up the football, and also John was in the playground. So the answer should be playground, which essentially is encoded in these two sentences. So the previous loss function obviously will not work because you have a single supporting fact, but the cool thing about this is you can iterate. Or in other words, the loss function might look something like this now. You start with the first supporting fact and you want to increase the score of your first supporting fact. Once that's done, you iterate and essentially combine that with your original question and want to increase the score of your second supporting fact. And finally, your final the output of your controller will take as input the original question and the two supporting facts, like the memories corresponding to the two supporting facts, and increase the score of those guys. So yeah, so basically, just to repeat, basically you have the first supporting fact, the second supporting fact, and finally you iterate. And this is what we call hops. And of course, they need not be limited to 2. You could sort of keep iterating until some threshold number of hops, and etc. Right. So like a slight digression right now, basically in order to test these models, so essentially we defined sort of 20 simulated tasks, where basically the objective of these tasks was to test models that can do complex reasoning in which involves long-term memory, but in a controlled environment. So why we wanted that, like think of these tasks as sort of unit tests in software engineering, right? Basically we wanted to sort of test skills of the models which like test one or at least two, maybe one or two skills in the model which sort of gives us an indication whether the model is doing any reasoning or not, right? And the skills could correspond to reasoning, it could correspond to language related skills like conjunction, co-reference, etc., and stuff like that. So I'll just quickly go through the collection of tasks that we came up with, which hopefully should give you an idea about, sort of convince you that probably this might be a good idea. So just to give you a bit of a background, so we essentially designed a simulator where a simulator had a bunch of objects like people and objects, and they had a bunch of actions, and each action was associated with an attribute, like a go would be go to a place, get would be get to an object, and so on and so forth, right? And based on this simulator, we came up with these sort of really simple scenario of a world where people are just moving around to one room or the other, picking up objects, dropping objects, and stuff like that, like Jason go kitchen, Jason get milk, and blah blah. And once we are given these commands, we had sort of a very simple templatized language which we plugged on top of this to convert these commands into natural language sentences. So again, the objective here was not to solve NLP, but to solve two things. One is basically to solve the reasoning bit given these commands, and also to have some sort of a language understanding skills, basically. Yeah. And we wanted all of this in a very controlled environment, and hence the simple simulation. So just to give you simple examples, the simplest of the example is basically a factoid based question answering, which uses only a single supporting fact, right? Where again the objective was, as we've seen so far, to answer a question given this story which has just a single supporting fact. And then an extension of that was a story which can only be answered, a question which can only be answered with 2 supporting facts, or a question which can only be answered with 3 supporting facts. And There was another task where basically we wanted to see if the model can learn the difference between two things, a subject and an object, where basically if the story looked something like the office is north of the bedroom is north of the bathroom, what is north of the bedroom, or what is the bedroom north of? So if you see, the two sentences have exactly the same words, but reordering them results in a different answer. So that was something we wanted to test, whether the model can actually differentiate between north and bedroom. And then similar to that, we had tasks related to 3-argument relation, where basically you have a story like Mary gave the cake to Fred, Fred gave the cake to Bill, Jeff was given the milk by Bill, and blah blah. And who gave the cake to Fred? And then a simple true-false questions, and questions pertaining to counting, like simple counting tasks, like Daniel picked up the football, he picked up the football, dropped the football, he got the milk, he got the apple, how many objects is Daniel holding? So here you see, like, if for the model to answer this, the model really needs to understand what's going on here. It's not like a simple input-output map in a black box where you expect this thing to be solved. And then there was tasks related to indefinite knowledge, where basically you're not given certain, like you're given some sort of an uncertain facts, and you're expected to answer and hence your answers could be something like maybe, like John is either in the classroom or the playground, and you ask, is John in the classroom? So things like that. And some language related tasks like basic co-reference. Daniel was in the kitchen, then he went to the studio, where is Daniel? Right, so it needs to understand what he meant here. And compound co-reference, Daniel and Sandra journeyed to the office, then they went to the garden, and then you want to answer, where is Daniel? Even though Sandra had moved to somewhere else. And like similar to that, we had other set of tasks like time manipulation, basic deduction, etc. But probably in the interest of time, I would move forward quickly. And then like positional reasoning about sizes, etc. and pathfinding and stuff like that. So yeah, so this gave us basically 20 tasks. Each task came with like a short story of this simulated world, and the model was expected to answer, and the questions were made so that basically you could evaluate if the model learns or not. And to compare our hypothesis that we really need an external context or an external memory, we compared with 3 sets of standard baseline. One is basically a standard structured SVM, where you have a whole bunch of hand-coded features from your story and your question, and you just want to predict an answer using an SVM. And we also used an LSTM, where basically we ran the LSTM over the entire story and the question, and the objective was to use the last hidden state of the LSTM to predict the final answer. And then a similar was an n-gram classifier, where again we took the story and the questions, represented it as a bag of n-grams, and then trained a classifier on top. So I guess you can see that. So you can see from this table, other than, I mean, the first and the third column were basically bound to be hopeless. Basically, the interesting bit is the LSTM, and as expected, since the story is long and it's the memory of the LSTM is fairly restricted to just one hidden vector, I mean, it did not do very well on most of the tasks, right? And compared to a memory network, which basically was the first version of the memory network consisting of 1 or 2 hops. So it does well on single supporting facts, 2 supporting facts, but does really poorly on the 3 supporting facts, and so on and so forth. And so in some of the tasks it works, some of them it does not work. And then, as I said, there's a lot of freedom in how you structure the memory network model, that you can play around with it. So the second version of this was with so-called adaptive memory, where essentially we do not restrict to 2 hops, but we define a special memory slot called the null memory slot and keep repeating the inference until it fetches the null memory slot and then generate an answer. And that, as expected, helps on 3 supporting facts and also on basic induction task, which I did not go into, but yeah, whatever. And then, as I said, like again, these are the next 2 are again variants of the memory networks, where how you encode the features. Instead of encoding as the whole sentence, we essentially treated a sentence as a bag of n-grams and used adaptive memory. And here we used adaptive memory and a nonlinear classifier instead of a simple scoring function at the end. And finally, a combination of all the 3. And we see as we increase the complexity of the network, the number of tasks it is able to solve successively increases, and each of these tasks are basically more complex than the other. Right. So that was basically the first version of our memory network that we proposed, and as I said, it's basically a fully supervised version, which means that during training, you're, in addition to the question, answer and the context, you're also given a supporting fact. So let's look a little deeper into what's happening here, right? Basically, we said that in the first step, we embed, or yeah, let's call this embed. We embed the story into the memories, and we also embed the given question into the memory, right? And then what we do is we match this question representation with all the slots in the memory to get these scores, right? These so-called relevance scores. Now think of the relevance scores, like think of these scores as how relevant each of these guys is to your current question, right? And then you're given a supporting fact, and basically you take that you take the slot corresponding to the correct supporting facts, and what you want is to retrieve this memory and to increase the score of this supporting fact and decrease the score of each of the other guys, right? So, and basically this is like a notion of hard attention, right? So each of these scores can be thought of as nothing but some sort of an yeah.
Do you know the memory where the correct answer is?
Sorry?
Do you know the memory where the correct answer is?
So as I said, in the fully supervised setting, during training, you do have that, right? So not during test. So yeah, so basically each of these scores, as I said, can be represented as some sort of a like how relevant that slot is to your current set of questions, right? And can be interpreted as some sort of an attention score, if you want, like how well you are confident that you really want to attend to that part of the memory. And then given the correct supporting fact, you essentially know that this score has to be higher, and you just pick that memory and push the score higher and decrease the other scores. So that's basically the idea of what, yeah.
On the previous slide, there was a pathfinding task that we set, and it didn't seem like any of the architectures did a very good job of
Yes.
pathfinding tasks.
Yes.
I was just wondering what exactly is pathfinding task and why is it so hard?
Yeah, so pathfinding task is basically like you're given a sequence of events, basically not really events, you're essentially given a layout of a sequence of rooms, if you want, like bathroom is north of the kitchen, bedroom is south of the bathroom, and so on and so forth. So that's the set of sentences you're given, and the question you're asked is, how do I go from bathroom to the kitchen? Right. So essentially, I mean, it's inherently a hard task, but because it really requires a lot of planning and search. Right. And sure enough, memory networks, at least the first version, are really bad at that. Or for that matter, like search is hard. Yeah. So as I said, as most of you have been sort of implicitly complaining by your questions, is what the hell are we doing with this fully supervised? Like, we don't really know during training time what the supporting fact is, right? That's certainly not a natural scenario. In a natural scenario, all you're given is a question, a story, and you want and you essentially want an answer. Or in other words, you want to learn which part of the memory is relevant to you even during training time, right? So sure enough, the second model which sort of tries to answer those questions is what we call an end-to-end memory network, where in this architecture the primary difference is that you're not given the initial supporting fact, and it actually learns the part of the memory which are relevant even during training, and this is achieved using the so-called soft attention. Like, again, by soft and hard, I mean in the hard case, since you were given what the correct memory is, which will correspond to the answer, you just pick that single memory. Whereas in the case of soft, you will probably have some sort of a score over your entire memory, and you will do some sort of a weighted combination and stuff like that. So again, like if attention is not super clear, I can definitely talk to you guys offline, and plus you'll hear a lot more about it in tomorrow's talk. So, and the cool thing about this is that the whole architecture is end-to-end differentiable, and it only needs supervision at the final output. So here's the architecture. Like, this is the single layer. So what you have is a question. As usual, you embed the question in whichever way you want. I mean, again, bag of words, output of an RNN, and blah blah. Let's denote it by U. And also you have your collection of sentences from the story which are embedded in your memory, again whichever way you want. You sort of match your U with these embeddings MIs to get the score PI, where PI is basically a softmax over your the scoring vector. So way to interpret the values of PI is basically how confident are you that this memory, that the ith memory slot is relevant to your question, right? And then you have the same set of sentences also embedded in this so-called output memory. Again, it's free for you to choose. You might as well share the parameters of the output and the input, in which case it will be the same matrix. If you want, you can keep it different, but again, like, that's more parameters in your model to learn, but whatever. So what you do is you use the PIs and the output of your collection of output memories to get your final output, which is basically a weighted sum of these memories weighted by the likelihood that that you were confident that the ith memory is your relevant memory. So that's your output, and finally you combine your O with your question representation U and pass it through some another parametric function to give you an answer, right? So if you look carefully at this architecture, this is basically a feed-forward net. I mean, you're going this way all the way up, and then you compute the loss, you go back. And during the process, you're learning your U's, you're learning your memories, and you're learning the matching scoring function, so that PIs are such that it picks up the relevant memory, and of course you're learning the final parametric function to give you the answer. So that's the end-to-end bit. Is it clear? Yeah. Yes, U is the question vector. Yeah. Again, it's just a dot product here. It could be anything. You could have a neural network. I mean, as long as.
But you are getting a probability distribution.
Yes, over the memories. So that's the soft bit of the attention, since you're getting like a distribution over your memories. So the cool thing about this is you can iterate. Where this is what I showed you in the previous slide. You have your question vector, you compute the output vector. You could combine the output vector with the previous question vector again and iterate, right? And keep going up until you want to go, and each of these steps is called a hop, and then you get a final output vector which you combine with the final question vector to generate an answer. So, I mean, you need this iteration again because of the fact that this will only select one fact, although it will be in a soft manner, but it will only select one fact, but you probably want to select multiple facts. And now if you look at it, basically this is nothing but an RNN turned sideways, right? Like if these matrices are shared, then this is nothing but an RNN which is turned on its side. Except for the fact that there is no limitation on the size of your memory. You're actually selectively picking memory or the bits of your RNN or your recurrent matrix which are most relevant to you for that time step, right? So that's the multiple hop end-to-end memory network. So here, yeah.
So even in a single hop case, you are actually doing a softmax over all the memory. So you are reasoning over multiple facts. So
Yeah, but
what's the difference between one and the other?
so this is just making that thing explicit. Like the single case almost always has the likelihood of picking only one slot in practice.
No, but you are like doing a soft addition over all the slots, right?
Sure. I mean, so think of it, right? Like consider that sequential statement. John went to the playground, John dropped the ball. And your question is, where is the ball, right? So there, in order to answer where is the ball, you really need to have some sort of a sequential processing. First you find out where the ball is, then you connect that ball with John, right? And in the single case, the softmax is taken independently over all the memories, right? So the hope is that in the first case you will pick one element of the sequence and then use that element to attend to the second element. Yeah.
When you're calculating the soft attention over the memory, so each memory is treated as independent.
Yes.
Would there be some maybe good idea for them to consider correlations between?
That's where, as I just explained, that's where the multiple hop things come in, right? I mean, where essentially you're tying your previous attention with the newer attention. Yeah.
How do you deal with multiple answers? For example, let's say you have a sentence, Alice likes ice cream and Bob likes donut, but not as much as ice cream, and the question is who likes ice cream? I mean, your Alice likes ice cream and your Emma will be higher than the Bob sentence, but how do you deal with that?
We don't.
You also will be
That's sort of one drawback. I mean, there are quite a few drawbacks which I'll talk about later.
so if this would be a single sentence with Alice and Bob likes ice cream, then you can use both.
No, I'm sorry. I thought you said how do we deal with multiple answers, or like a list of answers?
Yeah.
So I mean, right now we just pretend that a list of answer is a single answer. So if there are k answers, then you'll have like lots of potential answers, and then we try to train. So that's obviously not the best, but that's hard. That's really hard. Yeah.
So what's the reason of having a separate input and output memory instead of one?
So it will be clearer later on, where basically let's see. So I mean, the motivation is that the input memories are trained to generate your attention scores, and the output matrix is trained to predict the answer given the attention scores. Right? In some sense, the hope is that there will be some sort of a communication between the two. That said, in most of our experiments we shared them, but that was the motivation, because this never sees the final answer, right? This set of memories never see the final answer. And also I'll talk about later in this so-called key value pair, key value memory networks. Well, I don't know whether I'll be able to talk because it's I'm fairly late here, but the idea is this bit is used primarily for addressing which part of the memory is relevant, and this bit is used to actually, given that address, this bit is used to predict the answer. So you could store a different things here and a different thing in the corresponding ith slot in the output memory, which is more predictive to the answer. I think I should move ahead because there's a lot to go. So yeah, so as I said, the architecture is fairly flexible. You could use bag of words, you could use RNN style reading of words or characters to embed your questions and statements into the memory and things like that. And just to give you the set of experiments on the previous task, mem end-to-end are again far better than LSTMs, but as expected, not as well as a fully supervised memory networks, because of course there's less supervision, but still, I mean, they're pretty good. But they're but still, as I said, being not fully supervised, there are some tasks where it fails compared to the full supervision. And just to answer your question, why did we need multiple hops? Because consider this basic induction task, right? Brian is a frog, Lily is gray, Brian is yellow, Julius is green, Greg is a frog. What color is Greg? So first you need to know what basically what Greg is. So it attends in the first hop on what Greg is. Basically now it finds out it's okay, it's a frog. Then it attends what Brian is, who else is a frog. He says okay, fine, Brian is the frog, so it attends that, and then it says Brian is yellow. So that's the third hop where it is. So it needs that sequential reasoning, and of course it gives the correct answer. So and likewise on other tasks, right? So that was the sort of the performance on the so-called baby tasks. But as I said, it's basically an RNN turned on its side. So you might as well do language modeling and see whether it works or not, right? And basically the setup for a language modeling for mem-NNs is you're given a sequence of words, say the previous 100 words, you store each word in a memory slot, and you start with a null question vector, and then you do multiple hops. Basically null question vector, you do one hop, you get something, you concatenate with the question vector, you do another hop, and so on and so forth. Finally you get, after what, 6 or 7 hops, you get some feature vector, then you use that feature vector to predict the next word, right? So sort of putting this in RNN terms, what RNN is doing, and if you're aware of how the language modeling bit is done in RNN, you're given the current word, you do a single hop and produce the next word. Here the flexibility is that you can basically look at your context multiple times to generate your next word. And on standard data sets, namely Pentry Bank and Text 8, which is a subset of Wikipedia, we show that it performs fairly similar to LSTMs, which is the state of the art. Yeah.
Did you try using an adaptive number of hops based on some sort of confidence interval?
Yes, we did. I mean, not in this experiment, but for the baby task, yes. For the baby, yes, yeah. As I said, like we control the adaptation by the ability of the model to fetch the null memory. Once it fetches the null memory, we stop. So the conclusion from this experiment is that at least for language modeling, we may not really need long-term dependencies, because quite often in the case of language modeling, mostly it's like common words that you're predicting and you're computing the entropy over. But maybe once you're doing more, once you evaluate on nouns or entities, you might need long-term dependencies, right? Which is highly dependent on the document you're reading. So, and just to give you a brief overview of literature, as Yosha mentioned, that recently there's been a lot of work in these attention-based and memory-based models for numerous applications, like translation, I mean, for generating sort of strokes of characters, and then there's also the neural Turing machine, which I'll talk about given the time, assuming I have the time. And then there was also work on stack-based memories, which is fairly old. Let's move a bit quicker because there's a lot to cover. So then as I said, like I started off motivating how to deal with context which is super large, right? When suppose you have a knowledge base which has millions and millions of facts. So the cool thing about memory network again is that the architecture is fairly flexible. I never really mentioned how we are storing the memory. I mean, we can actually do some intelligence while storing the memory. In particular, you could hash the memories. You could hash the memories based on the words in the statement, in the sense, for instance, in the previous case, all the memories corresponding to Shaolin soccer would be in one bucket. All the memories corresponding to the god of cookery will be in another bucket, and so on and so forth, right? Because if you don't hash them, then there's like a million memory slots and it's kind of hard to do inference over, right? And the hashing could not only be with respect to words, but also it could be with respect to the embeddings of the words, and so on and so forth. And via this, we tried the model on actual question answering data set, which has about 14 million facts, which are stored in basically 14 million memory slots. And the statements are fairly diverse. Basically, you have stuff like this, and you have stuff like factual stuff, and you have stuff like, I mean, reasoning based. And yeah, and then basically we showed that mem-NNs with some fancy featureization basically gives you the state of the art, even on the large scale data set. And as I said, so without hashing, you're basically you have around 14 million memory slots. It gives you the best performance, but it's extremely slow at inference time, because you really need to score 14 million slots and pick the maximum. So if you hash by words or by clusters, you degrade in performance, but it's like significantly faster. So especially with clustering, you don't really degrade in performance much, but it's way faster, right? And then we also tried multitasking by using the real world question answering data set described in the previous slide and the baby tasks. And then at test time, we gave this cooked up story, and it could answer questions very in an interesting manner. Like some like simple factual questions like where is the story based questions like where is the milk, and it says office, and it could answer questions like where does the milk come from, it comes from cow. But in some cases are like the answers are nonsensical as well. So yeah, so I guess my point over here is that the architecture is fairly flexible, that what goes inside the memory is absolutely not restrictive. So another thing I want to go into detail is this so-called close style question answering. So the motivation is you want to build machines that can actually understand language, right? Basically, and one way to sort of know that a machine is understanding language is making it read a comprehension and making it answer questions that pertain only to the comprehension. Or in other words, the machine should not be able to answer questions based on some outside knowledge. So you want to restrict your questions in such a way that the answer exists in the story. Yeah, I think it was. Yeah. So, and unfortunately, there was no data set until recently that did this. No large scale data set, in fact, which you could use to train. I mean, there is a small data set like MC test and stuff, but it's really small and you can only use it for testing. So yeah, so I think this is an interesting problem, and recently there has been a couple of works in this direction, one from our lab and one from DeepMind, and where we've built the data set and models that does this, and they don't do a perfect job, but I think it's a step in the right direction. So in particular, we released this children's book data set where we took basically 118 books which were freely available and used snippets from this book to generate our comprehension and the question. In particular, we took the random 20 sentences from the book from anywhere. That's the context, and the 21st sentence is your question. And in that question, we basically remove a random word. And the task here is, given the story, fill in the blank. And as part of our training, we also provide a set of candidates to make things a little easier for the machine. And yeah, so the thing here is that you really want to remove the words which are not you really want to remove the words in a way so that simple models like language modeling type models are not able to answer these, right? In particular, the interesting set of words to remove from here would be entities that only appear here, or the nouns that only appear here, and so on and so forth, right? And the model is as usual. Basically, you have the story, you store the story in the memory, you have the question with the blank, you represent this in some way, and you score the memories and basically evaluate finally you score your candidates. And the novelty here is basically how we stored the memories. You could store the entire sentence, which we'll see in a bit was pretty bad. You could store word wise, like each word has its own slot, which is also bad. The best thing that worked was basically store windows of words. And basically these are the results. As you'll see, like language, so we split the columns in by the category of words we removed, like either the entity or common nouns or verbs or prepositions. So as you can see, models like LSTM, which essentially run through the whole story and predict the final answer after the story and the question, they do pretty well at verbs and prepositions because that's what language models do. But they are fairly bad at basically predicting the entities and nouns which are highly story dependent. Humans, by the way, do a very good job, which apparently was not evident from the earlier on in my talk, but it's okay. So these humans were basically annotators from Facebook. So we showed them the story, and they were given plenty of time to answer. So probably that's why they did a good job. And mem-NNs are there, not there yet, but yeah. So, well, I'll forget about self-supervision for now. And we tried the same model on the data set from DeepMind, which, as I said, is another very interesting work in this direction, where basically they use the news articles from CNN and Daily Mail. Probably you'll hear a lot more about this tomorrow as well. And each of these news articles comes with summary sentences, like snippets from the article. And what they do is, again, from that summary they remove one word, and then the setup is the same, that you want to predict the word given the news article and that summary article. So this is what it looks like. You're given the article, you are given the query where you remove some word. And to make the task harder so that language models fail, they actually anonymize these entities. So you don't really learn the model the BBC, you basically learn the model the blah, and that entity, this entity 381 will never appear anywhere else in the data, right? So you can't really learn the BBC. So, and yeah, so here again basically mem-NNs do a decent job until recently, where there were other results which sort of are better than this. Then as I said, there's dialogue modeling. Probably I'll skip dialogue modeling because the idea is similar. Like we released another data set in this direction where you could do question answering over movies, recommendation over movies, combining question answering and movie recommendation, and also a subset of the Reddit data which does free form dialogue modeling. Here basically the take home, the key point is basically you have two types of memories. One is this long term memory, which is essentially storing the background, the knowledge base, and then there is a short term memory which pertains to the dialogue that the model is having with the user. So you really need to combine this short term memory with this long term memory to answer questions that the user has asked. So details are in the paper, but I'll probably speed up. Lastly, as I said, there was this key value memory networks where, as I said before, the two matrices need not store the same thing. You could represent your triple, the knowledge base triple, which is basically subject relation object, as a key value pair where you define the key as subject and a relation and the value is your object. Because in the end, if somebody asks you a question relating to subject and relation, you really want the object to help you in answering and not the whole thing. So you could store a different thing here, and you use this as your addressing mechanism to focus towards which object is correct, and then use that addressing mechanism to fetch the actual object and use that to answer. So this is fairly recent actually. So I mean, yeah, and we show it does what it does. And then there was another paper called dynamic memory networks, which sort of emphasizes my point, which I've said that multiple times, that memory network architecture is fairly flexible. So this dynamic mem-NNs, what they do is really basically hammer the memory networks with recurrent networks everywhere. In particular, this is what the intimidating figure looks like. You have a question, you represent it with an RNN, you have the statements which also are represented by an RNN, well, the output of the RNN, and then given the question, you sort of score these representation to generate what you call these episodes, and that episode vector is combined with this so-called internal memory vector again via an RNN to generate the next memory vector. And you iterate using the current memory vector, the current question, you iterate to find another episode and plug that into the RNN, and so on and so forth. Finally, you get the final representation which you use to generate your answer. So, like if you think carefully, it's basically the same architecture, but with a lot more machinery into how you want to encode your data, right? Yeah, so and then basically they do reasonably well with such heavy machinery on the baby data set, right? So I will, and then they apply this to tasks like sentiment analysis and part of speech tagging and stuff like that. So I mean, I'm happy to discuss these offline after the talk if you guys are interested. So just to summarize, so basically memory networks are basically deep learning models that augment external memory, which is readable and writable, and these memories are learned and are effectively used for reasoning tasks, for language understanding tasks and stuff like that. And the architecture is quite flexible, as you know by now, to basically play around with stuff. The shortcomings are with the memory network model that I proposed, which I also spoke a bit about earlier, is that we don't really write into the memories intelligently, right? In the sense, we do not erase any memory. If we have a certain number of slots of memory, once the slots get full, we cycle. And we cannot compress memories. Like if we have like some long-term knowledge, there's no way to efficiently encode it so that later on it can be used in an efficient manner. It's just that every knowledge is treated the same, how recent or long-term back it is. So neural Turing machines, which I will talk briefly in 5 minutes, is basically an answer to some of the shortcomings of a memory network, where the architecture is, as I said, the same. The primary difference is in the way it writes into the memory, right? So the reading bit is very similar. Basically, you have a weight vector which is computed via your controller at time t, and that this weight is like your attention vector. And then for reading bit, all you're doing is taking all your memories and weighting them by the weight vector to get your final read vector out as output into your controller, which the controller will use for your final object for your final task. The write mechanism is a little more complicated, where basically you have the weight vector generated by the write module as before. Then it also generates 2 additional vectors, the erase and the add vector. So the first step in the write module, what the write head does is basically for every memory slot I, it multiplies it by this factor. So what essentially this is saying is, if the weight vector at I is 1 and the erase vector is also 1, then this memory slot is 0. So your current memory slot then becomes 0, like you've erased your memory. If the weight vector is 0, then you keep the previous memory. And then in the second step with this m tilde I hat, you essentially add your add vector, again weighted by that set of weights. So it's like a 2-step process, where in the first step it has erased the part of the memory that it wanted to and added the new information in the second step, right? So yeah, so the question here is, how do we compute the weight vectors? The cool thing about neural Turing machines is that the weight vectors are computed in a way that basically allows you to not just read or write at the next memory slot, but anywhere in your memory module. And that's achieved by combining the so-called content-based addressing and the location-based addressing. So the content-based addressing is basically the usual stuff that we've seen so far. Basically, you have the output of your controller KT, which could be your question, for instance, and you have the memory. Then you're essentially scoring each of your memories via the softmax. That gives you the weights of basically the content based scoring. And the location based scoring is a little more involved, and it involves 3 steps. The first step involves interpolating the previously computed content based scoring, the content based weighting in the previous slide, with the previous weights through some vector gt. Again, so this gt is the vector that your controller emits. And the second thing is convolving this WTG with some shift vector. So, and again, the shift vector is also the output of your controller, which essentially what this does, if you look carefully, is like if you allow shifts, say, well, essentially all it's doing is shifting the weights from from the jth location to the ith location, if you want, right? And lastly, since it's a convolution operation, and if the shift vector is basically smooth, then what this ends up doing is blurring the weight vector, so you probably need to sharpen it as well. And so in short, what these 3 steps lead to is a set of weight vectors I for the right module that could effectively write into a random memory slot, which probably you had already written to, or it could be a new slot or whatever. So that's pretty much it as far as the neural Turing machines is concerned. And the original paper used these models on simple tasks like copy, where you're given a sequence of vectors. The machine is expected to read the sequence, store the sequence in the memory, and sort of remember the sequence by generating it back again. So you can see that the LSTMs take quite a while. So if these are the number of epochs on the x-axis. So it takes quite a while to copy the even short sequences. I think this was tried. This graph is for a sequence of length 20, I believe, right? And the repeat copy is, as the name suggests, is basically you read the sequence once and repeat it k times. And here again, I mean, the neural Turing machines basically converge a lot faster. And whereas in the case of LSTM, it pretty much fails when it for large values of n being the number of times you want to repeat, right? And the sorting experiment was another one where basically you're given a collection of vectors and a set of priorities for the vectors, and you want to sort the vectors in the order of priority. So here again, basically neural Turing machines seem to successfully do that, and whereas LSTMs pretty much fail because like the entropy of the thingy is quite high. So yeah, so to summarize neural Turing machines, basically again sort of a deep network augmented with memory, where you can write into the memory much more intelligently than memory networks. And unfortunately, though, so far it has only been used for toy problems like copy, blah blah, and it was not scalable. So until recently, there's been some work from Yoshua's lab and also probably another one from DeepMind, where they've used it on the baby tasks at least, and show that the neural Turing machines do work there. And stack augmented RNNs I will skip because you will hear a lot more detail about them tomorrow. And so just to wrap up, so we discussed memory networks, which is basically, and we discussed the Turing machines, not so much the stack augmented RNNs, and we sort of gave you a quick overview of attention, both the soft and the hard version. but that's, I think, one of the cool things that has come out recently. But still, there's quite a bit lacking as far as these models are concerned. Like, we don't yet know what to write and what not to write. I mean, if you read a story, there may be so much of stuff that probably for us as humans, if you read a story, is sort of irrelevant, and you really don't want to keep that in your memory, only the selective bits. And what type of memory to use? Probably we have some answers in this direction, but not so much. How to forget, how to compress the old knowledge, we don't yet know. And basically how to build hierarchical memories where basically you can do multi-scale attention, for instance, and how to compose sort of learn intelligent composition functions for hierarchical reasoning and stuff like that. Those are the things that are still unanswered and basically open questions. So yeah, thank you.